It's a great honor to speak following the QED folks who I think are not just bringing some of the best ideas from around the world together, but also innovating and creating something which is unique in its quality and unique in its tailoredness to the needs of the students in India. So it's really exciting to be here and really exciting to work with you guys. So my talk is entitled Advancing the Science of Learning with Educational Data Mining. Is there a way to? Awesome. See if I can figure out how to use this. I'm not very good with technology. So we live in a world of big data, as Dr. Krishna's talk introduced. And every day we create tons and tons of big data with everything we do, whether it be walking with a pedometer or having meetings, using a cell phone, using a computer. And I'd like to start my discussion of big data with a discussion of cookies. Who here likes cookies? I only saw half the hands. I guess the other half of you don't like cookies. So, yeah, okay, fair enough. So in specific, I'd like to talk about internet browser cookies, which may not be quite as popular. They track everything you do on the internet. And my internet browser cookies happen to know everything there is to know about me. They know I'm fluent in English and Portuguese. They know I've got two little kids, Maria and Francisco. They know I'm a college professor. They know I read Kindle documents, but I do it on an iPad, which is kind of weird. They know I travel internationally for work. I like operas by Philip Glass. And I love Barney the Dinosaur and watch tons of Barney the Dinosaur videos online. It's definitely me, right? That's what my online profile says. And all this information, all this big data is used for the noble purpose of selling me more stuff. But the cool thing about big data is you can use it for more than just selling more stuff. You can use it to benefit science. And in the last decades, it's been used to benefit climate science. Here's a picture of the massive hurricane that hit my city about a year ago. It's been used to benefit physics, where literally billions, trillions, quadrillions of particle collisions are studied in order to find out about the basic nature of reality at laboratories like CERN and Fermilab. And in biology, where the professor here is a world expert in bioinformatics, which has helped to transform the practice of biological research and of medicine. And the moment's arriving where we can obtain and utilize similar amounts of data about education. One of the places where this has particularly happened in the United States is in the context of online learning, where more and more, in the early 80s, every American school got computers, pretty much, and so they said, hey, let's use this in school to try to create online learning experiences. And so we have things like Science Assistant / Inkits, which in many ways is taking the kind of things that QED does, putting them online. I personally don't think it's quite as exciting to watch a simulation of a bag inflating as to actually watch somebody do that kind of really impressively live. But there are online simulations where you can change the parameters of the simulation, change what you're experimenting with, and see what happens. And there are systems like EcoMove where you go around a world environment, picking up objects, talking to people, taking them to the lab. Again, not quite as rich as doing it live, but it creates a very scalable experience. Homework substitution systems, where instead of the kid doing their homework on paper and getting the answer the next day maybe from the teacher, the system actually in real time says, no, this is wrong and here's a hint. And systems like Zombie Division, where you learn math by killing skeletons, and Reasoning Mind, where math problems are embedded into story context. These have become increasingly popular in the United States especially, where systems like Reasoning Mind are used by the majority of kids in Texas, or Assessments over on the right are used by the majority of kids in Massachusetts and Maine. The great thing of these kind of systems is that every single thing the student does is logged. Every 5 seconds, whenever the student puts in an answer, the system is tracing it and tracing everything it means. That's a great source of data, but it's not the only source of educational data. You don't need educational data mining and learning analytics started with this kind of big data from online learning, but one of the exciting things about this day and age is how we're moving into other areas of data. For example, if you're giving kids assignments and you do it in the right way, the data can be entered in and you can use that to track student learning. Attitude and career surveys. Do folks use attitude and career surveys in India?
Yeah.
in America, they're very big as well. Every kid takes several of these throughout their schooling, and these systems try to predict what kind of careers you might be interested in. And long-term outcome data. So the National Student Clearinghouse in the United States actually tracks where every kid goes to college and what they major in. And student engagement data. This is a special treat here. This is data from yesterday. I'll talk a little bit later about how it was collected. But 2 members of QED went with me to schools and were able to collect data in real time. This data took about an hour and a half, 2 hours to collect, would you say, Viola? Yeah. About an hour and a half, 2 hours to determine that in the classrooms we studied, kids were spending about 40% of their time in passive participation, 40% active participation, and about 20% off task, which is pretty good. And that their emotions, about a third of the time they were either focused, that's a very positive affect state, bored, which is a less positive one. There was less at the far extremes and less in the middle. So this is formative data that we can use to say, how can we do better? Which activities are creating better engagement and are being more engaging to students? And this produces a lot of data. In 1 hour of traditional instruction, a student might produce 20 data points an hour from doing math problems or doing answering science questions. In an hour of traditional instruction, using the BROMP quantitative field observation protocol, which I'll talk about in a second, you might produce 8 data points. And one big advantage about this compared to very traditional approaches is if kids are doing assignments on paper, you actually, in order to analyze the data, you have to type it in somewhere. You have to get it in. Some human being has to enter it. With the BROMP protocol, which I'll talk about in a minute, the data is automatically logged, and you have it ready for analysis immediately. And in fact, it took me about, what would you guys say, about 10 minutes to make those graphs and analyze the data after the hour and a half of data collection. And a child using online learning for an hour might make 20 actions, each of which has 50 measured features, which is 10,000 data points. So the amount of data really grows very quickly. A lot of this data and its uses were pioneered in the Pittsburgh Science and Learning Center Data Shop, which is the world's leading public repository for educational software interaction data. And again, I think that there's a lot of great data beyond that, but this is kind of where the field started. That has over 250,000 hours of students using educational software within Learn Labs and other settings. 250,000 sounds like a lot, but in fact, if you look at the students that QED has currently served, you guys have already, if you had collected all the data with BROMP, you guys would have hundreds of thousands, if not millions of hours of data, when you consider every single kid is producing data separately. And this represents, in this kind of thing, over 30 million things that students did in online learning. And this amount of data has been supporting a revolution in the science of learning. Whereas before, education research had to be conducted using small amounts of data. For example, single studies in schools, which are, the researcher comes out and they do some lengthy process to investigate what's going on, and small numbers of researchers. Now we can have large amounts of data, which enable us to use the methods of data mining to find unexpected patterns. And data mining has been a revolution in trying to find things in data that we never even dreamed of, connections we never even thought possible. It's influenced lots of other fields, and today it's influencing education. Quick definition of educational data mining, or learning analytics as it's also called: the measurement, collection, analysis, and reporting of data about learners and their contexts for the purposes of understanding and optimizing learning and the environments in which it occurs. So the goal isn't just to study learning. And the goal of the science of learning I see not just as pure research, but as applied research, use-inspired pure research as well, that can try to help to really benefit education, learners, teachers, and administrators, and everybody involved in the educational system. And I like this quote because it comes from Art Gracer, who's the editor of the Journal of Educational Psychology, probably the most established scientific journal in the field, who said about 4 years ago that educational data mining is escalating the speed of research on many problems in education. Because not only can you look at the unique learning trajectories of individuals, but the sophistication of the models goes up enormously. And it's been great to see folks like Gracer, who's one of the leading figures in the science of learning in the 20th and early 21st centuries, getting so excited about this. So learning analytics and educational data mining communities have the joint goal of exploring the big data now available on Learners and Learning, to promote new scientific discoveries and advance the science of learning, to get better assessment of learners along multiple dimensions, not just, I got a lot louder all of a sudden, not just not just the kind of knowledge that can be measured with traditional standardized exams or skill, but also social aspects of learning, deeper cognition, emotion, metacognition, how students think about their learning, and at the individual, group, and institutional levels. And bring these together to have better support in real time for learners and more appropriate, more effective learning experiences. So in recent years, it's been possible to model a range of aspects of the learner, including knowledge, metacognition, engagement, and affect. And I'm going to focus on one of my group's projects and discuss some of our other work as I go. So in particular, I'm going to discuss our work to study student engagement during online learning, and then how we use this to predict other stuff that matters. And I'll make connections back to the situation of QUED and the situation of the kind of data that's easily available now with those kind of learning experiences. The context I'll be talking about is a system called assessments. That kind of that name comes from it assists as it assesses. I always trip up when I try to say that. It was developed by Neil Heffernan and Christina Heffernan in Massachusetts, and it's a web-based mathematics tutoring system, primarily for middle school math, that gives students mathematics questions. And when the students struggle, it offers them hints. So it doesn't just say you're wrong, it actually gives some hints about how to get the answer. And if a student makes an error, it even breaks down the problem into subproblems and scaffolds the student's cognition. It's a pretty good system, and it's been used by 50,000 kids a year in 2012, 2013. Now, after having just heard about 1 million kids using QUED, 50,000 may not sound like very much. What can I say? The United States is very fragmented in terms of learning systems. We have tons of competition. We've had tons of systems for 3 decades. 50,000 kids actually probably makes it the 3rd most widely used mathematics online software in the US. And as you can see, it's mostly in the northeastern United States. This is a good system. It leads to better learning than traditional homework. It leads to better learning than traditional classroom practice. It closes gaps in student learning. One of the big problems we have in the United States is that the rich get richer and the poor get poorer. Kids who come into middle school ahead of other kids get better, and kids who come into middle school behind other kids tend to get worse. And assessments closes these gaps and is very effective at doing that. And I'll talk about our work to model engagement assessments. We've also my lab has conducted research in over 20 other curriculum in a variety of domains, including middle school science, which I have done work both with QUED and with systems in the United States, introductory programming, database programming, high school math, elementary school math, medicine. Turns out that in the United States, at least, medical residents are the most disengaged group of students I've ever studied. It's kind of a little scary. It makes me worry about ever getting an operation, I'll tell you. Traditional elementary education, classical elementary education, and lots of other stuff. There are several perspectives on what engagement is. What is engagement? We have to think about what it is before we can really study it. There's at least 3 perspectives, including behavioral engagement, which is things like students' effort, their persistence, their attention, their participation, their involvement. Obviously, if a student is not involved in a learning situation, they're not going to learn as much as a student is actively participating. Cognitive engagement, which is how deeply kids are thinking about their learning, and emotional or affective engagement, which is the student's emotional reactions to the learning situation, including anxiety, boredom, happiness, focus. And I'll talk in particular about our work to study behavioral engagement and emotional and affective engagement. Both of these we've shown in some of our research to be really strongly correlated with things that matter. So a lot of the early work on this field from the 60s and 70s and 80s just said, is the kid on task or not? You know, is the kid actually participating at all, or are they not participating at all? And that was kind of the way the field was for 30 years. In the 90s, in a tradition that we've kind of adapted, people started to say, well, gee, it doesn't just matter if they're engaged at all or not, it matters how they're engaged. It matters how deeply they're engaged. And that's something I'm a strong believer in. In other words, if you're participating, but you're just going through the motions, not engaging very strongly, kind of bored, maybe even trying to just get the teacher to give you the answer, you're probably not going to learn as much as if you're really trying to learn. Some of the constructs we model in assessments included, first of all, off-task behavior. That's when a student disengages completely from the learning environment and task to engage in an unrelated behavior. And an example would be if the student's talking to another student about lungi, did I pronounce that right? Lungi dance. You know, I came to QUED with my example of what all the American students were talking about, One Direction, and everyone said, huh? every country's got a different thing, but there's always something that all the kids want to talk about, right? And so a student might be talking to another student about lungi dance, maybe reading a magazine about lungi dance, maybe surfing the web to read blog posts on the lungi dance. Maybe the student, on the other hand, is just sleeping in class. But you know, from what I'm understanding from our expert here, they're probably dreaming of lungi dance. It's nice that you know, cross-cultural things are so tricky, but it's nice that joke works everywhere on the planet. Another thing that's a big issue is gaming the system, where a student is intentionally subverting the educational system to try to get through without learning. In an online learning software, that might include systematic guessing. Maybe the student answers 1, and the software says you're wrong. So they try 2, and that's wrong. They try 3, 4, 5, all the way up to 38, and finally the system says, okay, go on, you're fine. A teacher wouldn't let a student try 38 answers, right? But on the other hand, teachers do often have a situation where if you have more than one teacher in the classroom, and I've seen that in some of the QED classrooms, a student will very strategically ask one teacher how to do one thing, and then the next teacher how to do the next thing, and then the third teacher do the next thing, and then go back to the first teacher, and just kind of systematically get all the answers and figure out how to get through without having to learn a single thing. Another thing we've studied is careless errors. That's making errors despite knowing the relevant skills or concepts. For example, if you add 2 plus 2 and you get 22, that's probably a careless error, at least if you're an adult. We also study affect, emotion, and context. Some of the affect that we found particularly meaningful in the United States includes what we call engaged concentration. You can also call it absorption, focus, flow, where you're focusing on the task and you're just really zoned into it. And that's actually very positive, which is great that the QED classrooms we studied had students a third of the time in flow. That's really kind of exciting. There's also boredom. I'll talk about this a little later, but boredom's really bad. Frustration. Everybody gets frustrated. Everybody gets confused sometimes. One interesting thing about frustration and confusion I'll talk about a little later is, whereas boredom is usually pretty much always bad, frustration and confusion, it depends on how and when you get frustrated and confused. If a kid's never confused, they're probably never learning, right? Everybody here had a little bit of confusion and surprise. Not everybody here. I heard one guess of one. But almost everybody here had a little bit of confusion and surprise with the demonstration of the airbag. It's good to be confused as long as you resolve it and as long as you learn from that. But you don't want a kid being frustrated for a half hour. They'll just give up. So there's a couple ways to assess this. And my group does both of the ways I'll be talking about. We start with his field observations, and in particular the BROMP, Baker-Rodrigo Observation Method Protocol, which we can conduct now through an Android app. So you can actually very quickly record data on student engagement through this process, and by doing it on an Android app, it's immediately in a very easy to analyze form, such that I was able to download the data and analyze it and make graphs in 5 minutes. And it's great. I think fast is so important in this day and age. We're in a fast world. It's a protocol that's designed to allow people to assess affect in a field setting, in real time, no video cameras, no fancy equipment except for the Android phone, and Android phones are getting cheaper and cheaper all the time. I understand there's even some versions built solely in India for India, and got to see some of those yesterday. I was very impressed. The goal is to get observations about the kid without disrupting the kid. You know, if you stand over the person you're observing, it's very distracting, right? You can tell I'm doing that. But if you do it in a different way, observing with peripheral vision or side glances, you're kind of got a blank expression right now, Krishna. You're not like smiling. Now you are. If you can observe with peripheral vision or side glances, hover over a student not being observed. So don't hover over the student you're observing, but, you know, kind of here I can observe Krishna pretty well out of the corner of my eye. And then do 20-second round robin, kind of going around the classroom, observations of a bunch of students. And the final thing that's really important is to look bored. Now, we don't want the kids to be bored, but here's the thing. If I'm standing up here looking energetic, you want to look at me. But if I stand here up here going, no one wants to look at somebody who looks like that. So if you look unhappy and bored, people don't look at you, and you can observe them much more easily. This method gets inter-rater reliability around, I don't know if folks are familiar with Cohen's kappa, but these numbers, 0.8 here is, if 0 is chance and 1 is perfect, 0.8 is 80% better than chance. So human coders can do 80% better than chance for behavior and 65% better than chance for affect and emotion. That's pretty good numbers. That's good enough to publish in a scientific journal. We've now trained 59 coders in the US, Philippines, and India. We've also done some work with it in Mexico. And it's been used for studying both offline and online learning. So we use it to study a variety of situations, and actually the situation it's most used for is for studying the teaching practices of elementary school kids in the United States. But I have a feeling that with QED, we're going to have we're going to quickly swamp all the data we've collected in the US up to this point. Oh, the pictures didn't come out very well. I apologize. What you would be seeing if I had taken better looking images is this is a picture of Haima observing a bunch of kids. What you can't quite see here is she's observing these kids, but she's looking like she's looking to the side. That's a really key thing about this method. You don't know that you're being watched when you're being watched. Kids know that they're being watched in general, but they don't know they're being watched right now. And by the way, the goal of this is not to, punish the kid, not to say, aha, we caught you. It's to, quietly take data on the efficacy of the learning situation that we can use in ways that matter. So let me show a quick picture of what the observed behavior looks like. I didn't have time to take a video here yesterday, but here's a video from some of our work in the United States. Can you click on it? I don't know how to. Well, oops. We could do. Oh, no codec. Well, what you would have been seeing is. I don't think we're gonna be able to install the codec in real time, so no worries, gentlemen. Thank you for trying. This would have just been a video of that gentleman there on the left making a massive yawn and fidgeting and shifting and trying not to look at his screen he was studying from. So Bromp observations are really quick to conduct. Once you're an expert in it, you can conduct an observation typically on the average every 8 seconds, which allows you to get a lot of data. They can be used at huge scale. I mean, one of the useful things is that since you can do it fast, you can get a lot of data. And they can also be used to develop automated models that recognize student engagement from log files of online learning, which is a lot of what I've done in the United States. Now, just using Bromp versus creating these automated models, why would you do one versus the other? Well, just using Bromp is usually completely preferable for offline classroom learning because we don't have the log files from the online software, or when observations are inexpensive. And automated detectors are preferable for when observations are expensive or impossible to do. So, for example, for homework, you can't stand over a kid's shoulder while they're doing homework in their house. They're nice if you can get them because they can enable very fine-grained analyses. You can infer exactly when the engagement changed. But when that's not feasible, the field observations are a very effective approach, and I think they will be very cost-effective here, just due to various factors about how much things cost in the two societies. When you do create the automated detectors, I'll just say a few words about it right now because it underlies the slides I'll be presenting in a few minutes. You synchronize the log data to the field observations by using the exact same time that both the hand device and the software the kids use is connected to the same time server. And then you distill meaningful features of the data for the learning environment and use data mining classification algorithms, and then validate the models on new kids. And I won't go into too much detail on the machine learning, because I understand this is mostly not an audience of computer scientists, right? So we assess the model by, I'll quickly talk about A prime, because I use that for a lot of things I'm going to talk about later. Imagine that you're trying to figure out if kids are bored, okay? And you have an urn of kids who are bored and an urn of kids who are not bored. You take one kid out of each urn, and you try to be able to tell which is which. That's A prime. So for example, if you have an A prime of 80% of 0.8, then you're able to tell 80% of the time between a bored kid and a non-bored kid. Is that clearish? Okay. Chance performance is 50% because that means you can tell half the time between the two. Perfect's 100%. And first level medical diagnostics, often 0.8 is good enough. I've seen papers in the 0.7s. By comparison, really good medical diagnostics get into the 0.9999 range. but that involves things like DNA PCR testing. And we validate all of our models by, again, building them on some students and testing them on data from entirely new students to make sure that they work on entirely new kids. And we did our work to build models of this, of engagement for assessments, using 505 kids in urban, rural, and suburban classrooms, involving demographics from very, very low income to average income. And what we got were models that could tell if a kid was off task or gaming system around 80%, and boredom around 63%. So 63% is not all that great, and yet the models that I'll show in a few minutes, we're still with quite a few things that matter. And why that's important is because think when I'm talking about the rest of the stuff I talk about today, think I made this on models that were only right 63% of the time, and BROMP is known to be more reliable. The only reason we use this, the automated models, is because it's a lot cheaper. But BROMP is more reliable than this, and yet we are still able to predict using the less reliable approach. One thing I should mention, by the way, is that models don't always generalize by culture, even in the United States. When you think about the massive cultural diversity in India, it's really important to keep in mind having observers from relatively similar cultural backgrounds. Even in the U.S., our models didn't transfer perfectly well between cities and rural areas. And so it's really important to obtain BROMP data from the cultures you're assessing to make sure your models are general. So it's nice to be able to detect a kid is bored. That's kind of cool, right? But does it really matter? Do we really care about it? In order to answer that question, we tried to use these models to predict other things. So for example, we tried to predict end-of-year learning. You folks, my understanding is there's end-of-year tests in India like in the United States. That's right? So end-of-year tests are big business in the United States. If a teacher's end-of-year scores are poor, the teacher might even end up getting fired. And often I think that's a really problematic thing because oftentimes it's not the teacher's fault. There are a lot of factors that play into that. But they are incredibly big business in the United States. And so we took models and we applied them to over 1,000 students who'd used the assessment system. And then we tried to predict how students would do on the standardized exam. And we found that students who gamed the system or who were bored were associated with significantly worse standardized exam scores. For those familiar with linear correlation, it was a linear correlation of about negative 0.4 for gaming the system and negative 0.25 for boredom. Students who were in engaged concentration a lot during the school had significantly better standardized exam scores. Off-task behavior had no association to learning at all. And that's an interesting thing because in the United States, at least, teachers pay very little attention to boredom or how seriously students are taking the learning, and a ton of attention to saying, be quiet, get back on task. And given that that doesn't even correlate to how well they do on the learning measures, that's kind of a problem, right? They're spending their time on the wrong things. Then we said, all right, how about longer-term outcomes? It's great that boredom during 6th grade predicts how you do on the 6th grade exam, but what about the future? So then we took data from 4,000 kids, and we said, can we predict who goes to college? In the United States, in our sample, only 58% of kids went to college. That's actually kind of good for the US. It's a real problem in the United States trying to get kids to go to college at all. For example, the Gates Foundation is putting lots of resources into solving that. How many kids went to a selective college? In other words, how many of them got a good placement? In the United States, college is very massively in quality, and we have some really amazing colleges in the United States and some really terrible ones. And finally, did the students major in STEM careers? Did they major in something that involves science, technology, engineering, and mathematics? We're very worried about in the United States about making sure to continue training students in these skills, because to a large degree, if you go to Silicon Valley, there's nobody who's American there. All the best people in Silicon Valley come from other places, and America really should be doing our part to contribute to the junior scientists of the world too, rather than just bringing the best. So for college attendance, student knowledge, as measured within the software, engaged concentration, and carelessness were associated with going to college. Now you might say, wait a minute, carelessness? That's kind of weird. Why do careless kids go to college more often? Part of the answer is because carelessness, at least in our sample, turns out to be the way that really smart kids disengage. So if kids are really smart and they know the material, then they're more likely to become careless. Gaming system, not attending school, and boredom were associated with not going to college. Now what's kind of interesting here is, just one sec. Um, yeah. Students who don't go to school, who don't even come to school, they're less likely to go to college. But it's an even better predictor whether they game the system when they're in school. So in other words, people don't come to school for a lot of reasons. They're sick, there are parental things, there are community things. There's a lot of reasons why people don't come to school a few days. That's not a good thing to not come to school, especially because a lot of kids who don't come to school, at least in the United States, are off goofing off on the street. But gaming the system, not taking your education seriously when you're in school, is even worse than just not coming to school at all after a certain point. How about good placement? The model's even better. We can tell from things in middle school about engagement and learning whether kids will get a good placement in college 76% of the time. And it's the exact same factors that are predictive. Student knowledge, engaged concentration, and carelessness are associated with going to college. Gaming the system, not attending school, and boredom associated with not going to college. And finally, college major. We can predict whether students will go into a science or math major from their engagement in math class 68% of the time from the exact same factors. So one of the interesting things is the exact same features of student engagement and learning are associated with going to college, going to a selective college, STEM college major, and if you went back earlier in the talk, how much you learn, how well you do on the state exams. So at least in the United States, it's really important to see, are kids gaming the system? Are they showing up to school? Even though it's not quite as big an effect as gaming the system, it's still a big effect. Are they getting bored in class? It's not so important. And also, are we creating engaged concentration? Because that's really good. It's not so important how much they're being on task or off task. Although, of course, at the extremes, if a kid's off task 80% of the time, that's a really big problem. But if they're taking an occasional break, it's not the biggest deal. You know, get them back on track and they'll be fine. So what that kind of ties as a takeaway message is, given the importance of boredom and engaged concentration, experiences like QEDS experiences that really engage students and get them focused are really important, but it's also really important to find ways to reduce the boredom that kids experience across learning situations. And this kind of analytics can be a tool for doing that because you can figure out exactly which learning activities are more boring and which ones are more engaging, and then fix the ones that are more boring. Nothing's perfect, and these kind of methods can be used for continuous improvement, much as corporations have been using for the last few decades. So how do we use this information to advance the science of learning, empower teachers, and provide automated intervention? So advancing science of learning. In fact, these kind of methods have been explosive in their impact on the science of learning. And there have been a lot of scientific discoveries across groups. One quick sample from my research group, just a few things we've done. So we've looked at the short-term impacts of affect in learning. I presented results on the longer-term impacts, you know, end-of-year exams and whether you go to college and whether you go to a good college. But in fact, we can also look at it minute by minute. One of the things we found was when we look at kids, extended confusion and frustration are bad. If a kid gets confused and frustrated and they never fix it, that's a really big problem. But brief confusion or frustration is good. If a kid is confused for 30 seconds, 20 seconds, that is part of what it means they're learning. So, and by the way, boredom is just bad no matter whether it's brief or long. It's always bad, at least in the States. One important conclusion for this is when you guys are going out and looking at the impacts of your activities, you know, it's good to look and see whether you're creating brief confusion experiences. That's a good thing. But then look to see whether the instructors, the teachers, are tying that back in, helping kids figure out what the answer is and why the thing works the way it does so that they are learning. And by the way, this research is both in live classrooms and in online stuff. So, another one is research on how the design of curriculum materials impact disengagement and affect. My group, including Lakshmi Dodonara, did some analyses where we found, for example, that very concrete mathematics problems are good for affect and engagement. So, for example, there was one mathematics problem where students have to figure out a set of equations in the context of understanding the Iditarod dog sled races in Alaska. And by the way, this isn't culturally relevant for kids in most of the United States any more than it would be here, but it's just such a fun, exciting story, and it gets kids thinking about riding these dog sleds, and this is very good for affect and engagement. Very abstract problems also turn out to be good for affect and engagement. Just giving kids sets of equations to solve and having it solved, that's also good. So what's bad? Stuff in between. Problems where there's a story, but it's a brief story, and it's not an engaging story at all. Like, Marcia bought 6 sweaters, and Jim bought 8 sweaters, and they paid $15. How much does each sweater cost? That kind of problem. Or a train leaves Coimbatore at 4 p.m. going 15 miles an hour, and a train leaves Chennai at 1 p.m. going 95 miles an hour, and what time will they pass each other? Those kind of problems, in the United States we call those hokey problems, and they're very disengaging to students. You either want to be pure math or you want to be rich math, at least in the States. And that was a finding that we were able to find in it, was influential in the design of some of the mathematics curriculum we work with. Another example would be studying the antecedents to eureka moments. So what you really want to create in education is moments where kids just get it, right? The light bulb goes on. They understand something they didn't before. And we were able to, even though they're rare, we were able to study these and figure out what preceded them. And we found that one of the big things that preceded them was when a kid pauses and tries to understand why they were wrong or tries to understand a hint. So getting told you're wrong or getting told a hint is not all that important in itself, but if you stop and pause and think about it, then you're much more likely to have a eureka moment soon. And that's something I think it can be useful across types of education. You know, if you're supporting a student, try to encourage your students to really stop and think about what they're learning. And so these are some of the scientific findings. These also can empower teachers. We can give teachers long-term information about where their students are going. You can know from this kind of data which students are likely to succeed more than you would just from who is doing well on the math problems or the science questions. But this is combined even with detailed formative information about why the child's at risk of not performing well. So it's not just this kid is in trouble, but it's this kid's in trouble because they're getting bored during these kinds of activities. And here's an example from some of our stuff. This is fake names here. But here's an example from some of our work with assessments where we actually have reports to parents on what students are succeeding on. And actually, this is a report for teachers. A report for teachers on what students are succeeding on and what they're not, and where they're getting disengaged. Assessments also has reports for parents where it actually sends a text message to parents when the kids didn't do things like turn in the homework or didn't take the homework seriously. Parents love that. Kids don't like it as much for some reason. And a third thing we do in online learning, and this is relevant to the kind of science club stuff, is automated intervention. When we found that kids were very likely to game the system in some of our online learning things, we created a little puppy character, Scooter the Tutor, who looked happy when kids were using the software appropriately and less happy when they were using it inappropriately. Kids love this, by the way, the boys especially. And Scooter, when students would miss learning something by gaming the system, would actually give them supplementary problems that covered the same stuff they just missed, another way to learn it. Or if you look at another way, evidence that they haven't learned it and something the teacher can see and say, hey, why are you getting these supplementary exercises? And traditionally with gaming the system, kids who game the system a lot start out below the rest of the class and they fall further behind by the post-test. But with Scooter, kids started behind the rest of the class, but they caught up by the post-test, which is a great finding. Unfortunately, the kids hated it in the United States. By the way, this is one of these important cultural factors. Kids loved it in the Philippines. Exact same intervention. US, they hated it. Philippines, they loved it. And in Latin America, it didn't even work at all because kids use the software totally differently. That's why, believe me, I'm not here to say this is what's right all around the world and you have to do this in India. I'm here to say, here are some things we've learned in America, and here are some tools you can use to investigate what's true and what's false in India, and come up with uniquely Indian solutions. Uniquely Tamil Nadu has appropriate solutions to your problems. So to give a kind of quick final vision, to bring this all together, and I really liked some of the way Krishna brought this together earlier. We can collect data faster than we ever did before, and get information about kids in real time. We can then analyze it quickly and get quick analytics, in a matter of minutes. And when they're finished building into some of their learning analytics systems, direct links between the handheld, the Brompt data, and the system, even immediately, immediate real data on what's working and what's not working, what kids are at risk, what kids are not at risk, which activities are being more effective than others. Get that information in the hands of teachers to help you guys who are teachers be more effective at knowing what kids need more attention and support and what they need, to help the designers of QED activities make better activities, and eventually to help every kid learn better, to create recommendations that can support teachers and help to engage every kid so that every kid can reach their full educational potential. That's what I really care about, and I think by being here, that's what you as teachers, researchers, administrators really care about. That's what we should be doing, to take these methods to revolutionize the science of learning and to revolutionize education. So finally, I'll give a little commercial at the end. If you liked what you heard and you're interested in finding out about some of our research results, all of our research results are on my webpage. Just Google Ryan Baker. I don't know what the top Ryan Baker is here. In the United States, there's some footballer who's a little more famous than me, but really a rock band. Okay. Well, I'm not that guy either. I am no rock star. You can also follow us on Twitter or on Facebook. We have a low traffic feed where we talk about our latest research results. I recently did a course, Big Data in Education, in Coursera. We're not going to repeat it in Coursera, long story, but 48,000 students learned from it, and we're going to have a YouTube archive of all the materials and a self-paced course available sometime this spring. And tell anybody who's interested, might be interested in our master's degree in cognitive studies with a focus on learning analytics at Teachers College Columbia. So if you're interested in learning more, read our papers, follow our materials. You can learn a lot from that. People around the world have. And maybe come join us in New York. It's been great to meet all of you, and thank you for coming.